unsaturated ketone. We've made those many times, but there's an extra piece to this. It's an annulation, which means we formed a ring. And a six-membered ring. So, when you see that combination, six-membered ring with alpha-beta unsaturated ketone, that should spark a memory of Robinson. Okay, and you should say, okay, well maybe I have to break that back and start with something that could have done an aldol condensation, right? Followed by, the last step would be the dehydration from the aldol condensation. Go backward all the way to Michael. So it's those three steps. Okay, so we're going to use that same logic here. It's a six-membered ring with alpha, beta, unsaturated ketone. It could be a much larger molecule. It could be a steroid. It could be fused to lots of other ring systems. But if you see that the new change was a six-membered ring with alpha, beta, unsaturated ketones, that means you did a Robinson. Okay, so over the arrow, if this was we just covered it, so I expect it to be pretty fresh, but if this was an exam, you would have had, your base pairing, like KOH or something in water, maybe even some heat. So this would be your reagents. You need the base, you need the protosolvent to do your Michael reaction, your aldol condensation, and dehydration. Okay, so by the time you get to the exam, you want to be able to say, okay, well I know that I started with this, and...
Professor, can you move it down, please?
Sorry about that, yes. You want to be able to say I started with those two, that's how I got it. Now how do you reason through that? Yes?
I think it's going to need protonate on one side instead of the other.
I forgot a carbon. One side instead of the other. So if we go back, there are other ways that these products can form, but what you kind of want to look for is whatever was, so notice this is you start off with a Michael, right, for this one, for example, and so then later your Michael was left alone, and your other H came from this side, so it came from this one. And then when you're all done, the last H, so you had to dehydrate, right? The last H came from, I got it kind of superimposed here, right here. So, my arrows got messed up when I moved this, huh? Where did this go? So we had we protonated that, then we had our H stuck on the methyl. Aha. It's annoying when I did that. Okay, so then if I trace, if you want to circle them with me, we can trace our H's, because that's an important question, is what H's did we use? So in green, this was a crucial H. That H was used for dehydration. Okay, so that formed our alkene. Okay. Now, this sneaky thing, gotta move those with my two fingers together. I've never had that happen once before, and I don't know what I do to cause that, but I think I can deal with it. Okay, now let's find the other H that had to be there. I'll use green again. So we had to make that second enolate. So going back, this was a mandatory H on there. So is this the step you're asking about, Valley? Why don't we take off this side?
Yeah, that one and the first one.
Well, this one would not let us get a six-membered ring, right? So we always make those same sorts of decisions. Why this H and not that one? we need a 6-membered ring. So if I number starting here, 1 as my alpha proton, 2, 3, 4, right? Or 1, 2, 3, 4. So remember, whatever alpha proton you're taking is going to attack the carbonyl on the other piece. And so you want to make a good ring size. So it needs to be this guy. So you need an alpha H on the side of the carbonyl that will allow you to have a 6-membered ring. So notice that that alpha H, when we trace it back, that's our second H that we required. Okay. We have a third H that's required, as you can see in the template at the top box. So let's see if I can move. Come on. Put this back. Put both fingers on there. I'll move it down. Okay, other H that's required is the very first step. So this one was a choice because it was the most acidic proton. Okay, so we formed an enolate there. So notice that on that one, on this guy, we only used one of the H's. On this guy, we used 2. We used the 2 that were over here. That's the pattern in a Robinson. In the Robinson, you find your Michael acceptor, and you're going to use those 2 H's. You find your Michael donor, and you're going to use 1 H. So it's 2 from the acceptor, 1 from the donor. So that's the pattern outlined here. Okay, 2 from the acceptor, 1 from the donor. It's easier to see from the starting materials because you can't even pick this other side. This is not a valid alpha H. It's a vinylic H. Your alpha H's have to be on sp3 hybridized carbons. So you take 2 off of this guy and 1 from here, and you might have to make a choice if there's more than 1 carbonyl. It's good to pick the one that's the most acidic to drive it forward. Okay, so let's apply that reasoning to a different structure, also using a Robinson. How would we get those pieces? I think it's easiest to work backward. So there's a lot of space on here for that reason. So if I give myself some room, I'm gonna show my reasoning in blue here. Okay, so I'll redraw the molecule because I'm gonna start highlighting a few key pieces of it. And so I have my alpha beta unsaturated carbonyl and a 6-membered ring. And if I remember the 3 steps of the Robinson, it's Michael aldol dehydration, right? So if I'm trying to work backwards, I'm thinking dehydration, aldol, Michael, okay? So think back to the dehydration step. So forward was minus water. So what did it look like before we lost the water? Well, that's how we got the alkene, right? It's from dehydration. So the question is, where was the H and where was the OH? Well, the OH had to be here because that used to be a carbonyl that this enolate attacked, right? And this was an alpha H that got removed to dehydrate. And that logic that I used to help determine where that was is also what I'm going to use to help determine how my aldol was performed. So to do my aldol, that means this is the new bond for the aldol step. So something attacked something else, forming that alcohol. What do we attack to form an alcohol? Carbonyl. So that oxygen is now a carbonyl, part of a carbonyl. That's my ring forming step. Gotta go back. I like to draw it in the same, almost ring-like conformation, just to keep it clear. But here, so we had to have. This used to be my enolates right here. I'll put my anion more directly on that carbon right there. And then my carbonyl is there. With practice, you can probably actually just go straight to that step. you know, you realize that the pi bond part of the Robinson has a carbonyl on one side and enolate on the other, right? So that's what we did there. But it doesn't hurt to do it stepwise if that helps. Okay, so then if you need to, go back to where it's completely neutral just to make it extra clear, because you know, skipping steps in the very first stages of studying is not always easy, but you know, you want to get to a point where you can assume it was, that's when you deprotonated it, right? So that's when you added the base. Okay, so it was neutral at some point before we did the Michael. So how do we do the Michael? So the Michael, remember, if you kind of remember that pattern I was talking to you about, the Robinson pattern is that we use so we've used 2 alpha protons so far, 1, and then a second one here, right? So these 2 have already been used up. Those were these same guys here. That one, right? So we lost both of those green H's at some point along the way. What was on the other side? The 2 alpha H's came from the Michael acceptor, right? So that means this is the alpha proton side, this is the alkene side, alpha beta unsaturated ketone, what you start with for a Michael. So I have to label this alpha beta, so I don't cut off the wrong one. That means I can cut off right after beta to disconnect and figure out where my starting material used to be. So that means that the previous step leading up to this is probably the most challenging one, is to visualize the Michael. So if this step's hard, hopefully it will become easier when you do more practice with just the Michael reaction alone. But that alpha beta was labeled so that we remember to make that alpha beta unsaturated ketone, plus the other piece, which was our first enolate, and the only time that one got to be enolate. So that matches what I put in the box, it's just flipped around a little. Okay, but you want to be able to use that reasoning to work your way back. You can also kind of highlight these pieces. I think that's sometimes helpful too. Let's see, what color I might not use, maybe some black. If I say, okay, well, and you know, counting carbons also helps, but color coding is also useful. So where did that piece come from? In my very first starting material, or not really actually my product, but I'm working with the backward problem. So where did that piece come from? Well, that's this piece here, right? So alpha, beta, include that carbon. And let's do a red color. So that means this piece, you want to making sure I account for all my carbons. Came from here. You can see my missing oxygen that I lost during the dehydration step. That's where the carbonyl is, right? This looks practically the same structurally, it's just missing the pi bond right there. So lots of levels of the pattern to follow. So it's not a simple one. You've got to spend some time on it. Okay, any more questions on Robinson? We are going to, our plan for a workshop today, aside from maybe a couple new amine problems, is to, and you know, as well as Friday, is we're going to do, I have some yellow paper. We're going to do some roadmaps. So if you feel like that's going to spoil your studying, which I do actually think it does a little bit, but I want to do it for this chapter because if it's not organized in some way with patterns, you know, it really could be distilled to some simple themes. It's going to be a very difficult one to get through. So you could use mine as a guide, but I still urge you to kind of come up with your own, especially if you have a Friday workshop, and then maybe use mine and look at mine again to see if it matches, or tweak yours to see if you want to use any elements of mine. I never claim that mine's exhaustive, so you can always add notes to mine and work with it as you see fit. But I think this is a chapter where it's going to be particularly useful to make a roadmap, because it's actually not a ton of reactions. It's how to know what slot to put those in. It's a sorting sort of chapter, where this one goes here, this one goes here, this one goes here, and it's done with some pretty subtle conceptual pattern recognition for the most part. Okay, so that wraps up chapter 21. This is a very important chapter to do homework on, so do homework like crazy. Also look at don't be afraid of that second language book. There's nothing wrong with it. It can help clarify some things. So if you've done the chapter 21 homework or it seems insurmountable, start there. It's really good for drills. So if you feel like you're weak with Michael reactions, for example, it's good at having a list of just those, rather than having a lot of conceptual wordiness to kind of set up the problem. So give those a try, because we're going to keep moving on to amines. And this is our last chapter, actually, that's functional group based. The other chapters are more based on the goal of what we're doing. So we have a couple biochem chapters that are more like intro to biochem, that in the sense that it overlaps with organic. And we also have a carbon-carbon bond forming organometallic chapter. So this is our last chapter that's just a collection of functional groups. So amines play a big role, biologically speaking. You hear about them all the time in amino acids, which will get its own chapter soon enough. But just some well-known amines are shown here. So you can imagine that these amine reactions that we're about to learn, they're really important, especially in the pharmaceutical industry. You can see that they form as primary, secondary, tertiary cyclic amines. We also get, in the same chapter, we're also going to cover, go back to imines, right? So pi bonds to amines and so on. So this is a good time to think back and pat yourself on the back. You've learned a lot of different functional groups and reactions to interconvert them all, and just kind of put it in perspective. These are the 21 that we cover in our year of organic chemistry. And so you can see we've done a lot of reactions with them, and I'll just highlight some of the themes. When we had alkenes and alkynes back into 11, if we were going to do a reaction, we did an addition reaction, right? But if we were going to do, have the pi bonds in a ring, we learned in 211, we weren't touching benzene with those addition reactions. We learned in 212 that they had their own category. So that's where electrophilic aromatic substitution, SNAR, we had, the Birch reduction, those all came into play. And by the way, chapter 22, you've done the tail end of it, has a little bit of that in terms of the diazo, the 6-diazonium reactions. So we're not repeating that, we're just doing the new part. So the part that was already on exam 2 will not be on exam 3. Just the rest of this chapter will be. So back to 211, remember alkyl halides. We're good for SN1, SN2, E1, E2. And alcohols mostly had acid-base properties before we could use them in a reaction. Same with ethers, so these are oxygen functional groups. Epoxides, remember those? Back from 211, we did a lot of ring opening and closing to form them. And they had their SN1 or SN2 hybrid mechanism, depending on whether we were using acid or base. I'm kind of doing this on purpose because I know that it's a cumulative class, and especially the final. So it's kind of good to reestablish some of these fundamentals. And some of them come up again in this chapter, which is good timing as we get closer to the end. So ring open, opening, alcohols we learned to treat similar to alcohols, and sulfides were similar to ethers, also known as a thioether, for that reason. Disulfides have some biochem relevance, so we'll actually pay a little more attention to them in those chapters. And then can't forget our hefty carbonyl section, where we organized all of our reactions by the attack open close kick mechanism, where we have substitution and retain our carbonyl, or attack open protonate, where we have a new group come in and lose our carbonyl to an alcohol, becomes an alcohol. We mostly use nitros. Well, now I'm getting to the nitrogen functional groups down at the bottom. They're kind of organized in order of what atom is the key feature. So I might actually do this in a different color simply because that is this chapter. So remember, nitros, we reduce with a hydrogen source to amines. That's important because we're using amines in this chapter. So you need to be able to start with amines or get to them from a nitro. Same with nitriles, reduce, but we also saw nitriles were part of this carbonyl chunk, but I give it its own box because it also has amine significance. So you could reduce or do the alpha attack, similar to carbonyl. We've seen that imines, like nitriles, also reduce to amines. And now this is what we're going to do for this chapter. So what chapter are we in again? 22. That's 3rd edition Klein, is 22. So we're going to be learning all the arrows to go make an amine, react an amine, okay? And then use some of our previous functional groups to get there as well, like nitro, imine, nitrile. Okay. In order to understand the reactions that are coming, it helps to remember the structure-function relationship of the amine functional group. What did we usually use amines for in the past? Even back into 102, you used an amine. Used ammonia quite regularly. What did you use it for? A base. So that lone pair here, let's see, what's black, allows it to act as a Lewis base. So remember, Lewis base can mean a Bronsted-Lowry base. Lewis base can also mean a nucleophile, where it attacks something other than a proton. Okay, so that's going to be the theme in our mechanisms. We're going to be using that lone pair. Okay, so that should be a common feature. Don't do anything else that's surprising. It's going to make sense because that lone pair is electron rich. Since we are using amines, this is the time where your nomenclature homework problems will start popping up. It's pretty straightforward except for one new piece that's a little unusual. And that's because amines can actually form more than one bond to another carbon group. So it makes 3 bonds, right? If we want to identify the number of methyls on here, and we want to distinguish the ones that are on the nitrogen versus the carbon, we use the prefix N. So we'll do an example. The suffix amine, we've probably seen many times, like hexanamine, right? So 6 carbon chain with an amine. So let's, if it's a prefix because it's lower priority, then we use amino. I'll write that out. That's usually on your chart, but I'm not going to spend too much time on naming other than this unusual case. Okay, so remember we use a prefix if N is lower priority. Okay, so let's figure out the best way to name this. We got to get the parent name first, the longest chain of carbon atoms. So we could start here, 1, 2, 3, 4, 5, 6. Okay, so 6 carbon atoms. Is that the best way to number? there a better way? Well, why did I start at the left? Could have started at the right. 1, 2, 3, 4, 5, 6. Remember, I have to think about, I'm going to name the functional groups. The amine is a functional group. I want to give the lowest number possible. So 2, 3, 4 in red versus a 3, 4, 5 list of functional groups or substituents means the red path is going to be the correct way to name, right? Okay, so now I can start naming. My parent chain has 6 carbons, so it's going to be hexane. There's no alkenes or alkynes, so hexane, amine. Where is my amine? Since amine made it to the suffix, I have to put a number before that to tell everybody where my amine was. My amine was on carbon 3. Now I need to talk about all those methyls. How many methyls are there? 1, 2, 3, 4, right? 4 methyls. So I need to use tetra to describe that I have 4 methyls. So tetramethyl. I'm going to run out of space here. Let's see. That's the hard part about working backwards, although it's always my preferred way. I often run out of space. There we go. Tetramethyl. Now I have to name where those methyls are. So before we had amines, we would just name the carbon numbers and say, okay, 2 and 4 have the methyls. But we also have 2 methyls on the nitrogen. And the nitrogen didn't get a number. That's where the N comes in. So 2 are on nitrogen, 2 are on carbons. So I need 4 descriptors. So I need an N and N, and a number and a number. Okay, so N, N, and then my red numbers I remember are what, 1 out, so it's going to be 2, 4. Now if you did 2, 4, NN, or NN, 2, 4, or 2N, 4N, I don't care about that, because no matter what, how you did that order, you would get that, and only that molecule drawn out, right? So that N is the new piece of the naming puzzle. Everything else is kind of the same logic. Okay, any questions on the IUPAC naming for amines? Okay, you might want to practice some other ones that you see in your homework. Okay, so once again, keeping it simple, when we start off our amine reactions, kind of think of it as having 2 possible roles. Think of the nitrogen as acting as a Bronsted-Lowry participant in acid-base reaction. So you always find this for example is aniline, the amine with benzene attached, very common one. You probably saw that common name a lot in your aromatic chapter. Aniline is a well-known organic base. If it's in the presence of an acid, which acetic acid is an acid, then we simply have an acid-base reaction. It's actually kind of boring, so that's not usually the goal for this chapter, but it's something to keep in mind because in our mechanistic steps, we will sometimes need a base. We'll be looking for a base. So yeah, and the amine is present. We'll go reuse that as our base, just like in our alcohol section. We might have been doing some other business with the alcohol, but in the mechanism, if we needed a base, we can go back and use the OH base. Okay, so the other, as you probably guessed, something that could be a base can also be a nucleophile that, in other words, a Lewis base, something that attacks something other than a proton. So here you could see the lone pair is still there, but we don't have the protic reagent present. So instead of attacking an H, it's going to attack that delta plus on the carbon. Attack, open, and we've actually done this before, right? Acid chloride. So I might even just extend this since it's review. Open, close, kick. This is how we made amides. So we've done reactions with amines. But you might just remember, oh, well, somewhere along the line I had that proton there, I had to neutralize it, so we'll see some of those steps in our mechanisms. And to start off this, I don't go in exactly, I cover the reactions Klein covers, but I don't go in exactly the same order. I like to start off with some of our review reactions. And so it's new mixed with old. So before I introduce what's called the Hoffman elimination using an amine, you might remember the Hoffman name from 211. So where did Hoffman come in? Zaitsev's nemesis, basically, right? This old slide from 211. So just to remind you, you don't have to have this slide because I'm going to summarize it all, but Zaitsev told us the rule that if you have an alkene that you're going to form in an E2 reaction, the major is more substituted. So look at our starting materials. This is 211 stuff. It's a good time to review it because it's actually kind of the bread and butter of organic to understand elimination. So leaving group, pretty simple looking substrate. Pretty small, regular old base, but strong base. We do an E2. We do not see as much of the Hoffman product. We see more of the Zaitsev product. But of course, chemists, they really like to break the rules. So if they say, okay, there's a rule, let's see if we can break it. They want to say, how can we force the Hoffman to be major? So what you learned back in 211, and so it's named after August Wilhelm von Hoffman, is that if you have a bulkier base, and usually it's even more outrageously bulky than this, screaming in your face bulky, must be steric hindrance at play, coupled with ideally a bulkier substrate. So notice we have the isopropyl group in there. So it's harder to get into the interior where there might be an H that could come off and give you the Zaitsev product, because remember Zaitsev's more substituted. In order to achieve a Zaitsev alkene, you actually have to have a base that can get in there, right? So if you couple bulky with bulky, you actually can find a way to favor the Hoffman alkene. There's another way that's being introduced in this chapter using amines. Okay, so this is called the Hoffman elimination. So I know you have a little bit of room at the margin. It should have had a title. Did it get chopped off? This is called, okay, I'll write it up here. This won't be nicely typed. Hoffman. Thank you. Elimination. Okay, Hoffman elimination is going to give us a Hoffman product by starting with an amine and making our substrate bulky with a bulky leaving group. So I'll write that out. So you modify amine to, remember an amine is a bad leaving group. So there's that issue too. So to get one, a good leaving group, and two, a bulky leaving group. So those things together allow us, now that you have a good leaving group, allows you to do an elimination. And the fact that it's bulky allows you to get the least substituted alkene, hence the name Hoffman product.
Can you go back a little bit?
Oh yeah, sorry. So you get the least substituted, i.e. Hoffman alkene. Okay, so notice the difference. We don't have leaving groups. So from 211, we had a leaving group to do an elimination. Amine is not a leaving group. So your first step is to turn it into a leaving group. The way you turn amines into a leaving group is similar to the way you turn, we've done it before, OH into a leaving group. We make water. What could we make with an amine? So if we make the hydronium with alcohol, with an amine we make ammonium. So if you can make an ammonium ion, it's happy to leave. So we do that with over-alkylation. So to alkylate the amine, we have our simple alkyl halide, methyl iodide, lone pair attacks, there's excess. It does it until it's completely filled up. So nothing, no more lone pairs left to attack. Okay, it'll lose protons until it's completely full. Okay, so I will draw out, I'm not going to draw the mechanism of this after this, but I will do it this one time because we know it's actually a simple series of substitutions. But for the first time, since we will just take advantage of that fact, we're going to do it the whole thing. So remember, this is a substitution reaction. So we have a lone pair, and we've done SN2s with amines back in 211. So remember, this is the electrophilic carbon due to the fact that we have a highly polar bond. Iodine's a good leaving group. So we're going to do substitutions repeatedly. Attack, leave. And then I'm just going to draw out over on the side, margin. So we have 2 H's and a methyl, and it's positively charged. But we have excess methyl iodide, so we can replace those H's with methyls. But to show that in the mechanism, we have to get rid of the H first, an H at a time. And so to do that, we need a base. Who's going to be our base? More of the amine. So just when the amine can act as a nucleophile, that's kind of why we reviewed that. So it can also act as a base. I'm just going to say RNH2. That's more of the starting material coming along. This is just a neutralization step. And H. Now we have our neutral amine. We have our lone pair back. Okay, what can that lone pair do? Attack another equivalent of methyl iodide. I'll just take up this spot down here. CH3I. So we're in the same boat we were before. We have an ammonium ion that can be neutralized by the presence of more amine. So it's just a repeat of the previous step. At last, we have no more hydrogens left. We have just a lone pair. It'll do its final alkylation. Okay, so I'm not going to draw the MEs anymore. I'm just going to draw them as lines because that's how we'll usually see them. Okay, so at last, it cannot be neutralized. It's stuck as an ammonium, right? There's no more H's to take off. It's completely methylated. It's stuck as an ammonium. So now it's a very good leaving group. Okay, so that's what I'm going to draw here. I'll just draw, that's the product of the first reaction. So I'll draw it right here. So when you have an amine in the presence of excess methyl iodide, or methyl bromide, something of that nature, then you can over-alkylate it to the point where it's now an ammonium ion, i.e. good leaving group. So it's safe to throw a base in there because the base can't pull off any protons, it's completely alkylated. The base will instead pull off a proton from a carbon. Okay, so hydroxide's what I see used in many, many sources. Klein also throws in another popular way to generate hydroxide, which will look unusual at first, because usually we just have KOH, NaOH. But he introduces this silver oxide water mixture, which is another source of hydroxide, strong base. But don't let that catch you off guard. It's nothing fancy, it's just hydroxide. It's just a popular reagent for Hoffman elimination in general. Okay, so we throw in source of hydroxide. We can do an elimination. Remember how to do an elimination? We have to take an H on the next carbon over to where the leaving group is. So here's our leaving group. So we have to take, this is the carbon that has the leaving group. We can take one from here, right? We can take one from here, we can take one from here. So if the leaving group was alpha with a carbon, okay, we then call the adjacent carbons beta. So that's why it's called beta elimination, right? So from this point on, it's 211 stuff again. So we could take our H here, here, here. I'll draw them all in. Remember the goal in 211 when we were using a small base like that was to get the Zaitsev product. But seeing as this is the Hoffman elimination, we're likely not going to get the Zaitsev product. So if I number these H's, 1, 2, 3, which H is coming off? 2. The least substituted alkene will be formed because our leaving group is so sterically hindered, it makes our substrate too sterically hindered to access those interior protons. The exterior peripheral protons are easier for the base to get to. So we have our hydroxide, do an E2, all in one step, inserted. There we go, our least substituted alkene. Sometimes there's a little hint. If you're doing an exam problem where it says predict the product, the missing product, you might see the byproduct, the amine that came off. It's now neutral. Yes?
How will you got the H number 2? Because in the intermediate isn't metal.
Yeah, so methyl has 3 H's on it, right? I only drew one of the 3. So this is an extra, this is a bond,
Oh, okay.
right?
Okay, yeah.
Yeah, I know.
didn't
So,
know that it's a bond. I thought you just-
well, you know, that's a normal point of confusion is to see those exo to the ring H's. They're there. For some reason, no one wants to see them. It's really common, actually, so don't feel bad. That's a good thing that you brought that up. Okay, now I'm going to bring back another example. Let's say we just went ahead and did, usually you'll see this represented as 2 steps over an arrow. Start with your amine, step 1, step 2, get to your alkene. I want to focus on this last step because it demands a little bit of review. And I'm going to do it in 2 ways. So we're going to start part A, and I'm going to redraw this substrate to do, let's see, what did I change here? Keep that the same. I'm going to block aside, bless you. So instead of a methyl, I'll have a T-butyl. So that'll just give us some different scenarios to think about encountering. Otherwise, it's the same. And just to keep it in our heads that we could use either method, I'll add the silver oxide mixed with water. Okay, so the only difference between those 2, other than what's written over the arrow, which are both sources of hydroxide, is that the amine is flanked by a primary R group on the right, as opposed to a tertiary R group on the right. All right, so let's do the first example. we are assuming we can safely get to this point, starting with an amine, the overalkylated amine would be a good leaving group. Now it's an ammonium. We have to find our beta H's. So we don't look at the H here. We look at the H on the two adjacent carbons, just like we did back in 211. So we draw those in. So this is a methyl. Just have those 3 H's. You only really need to draw in one, but just for clarity this time, I'll draw on the other one. Now on the other side, since we have a stereocenter, we have an H that's on the dash. All right, so Hoffman, least substituted alkene. Do we want to take the methyl H off or the methylene, that's the interior H off? Well, this is bulky, making the interior less accessible, so the base can more easily get to these, right? So this is really coming down to a case of kinetics versus thermodynamics, right? Because Zaitsev is thermodynamically the most stable alkene, but if you block it, so it's harder to get to, then by using a bulky leaving group, then you end up forcing the kinetic product to be major. Okay, so we're going to do an E2. Take off the peripheral proton and concerted steps of arrows. Means they all happen in one structure for the mechanism at one time. So my product looks like this. We're simply doing an E2. But remember, if I block one of the possible protons, we just have to do the other route. That's the only possible elimination product. Okay, so even though previously we had a choice between Zaitsev and Hoffman, here, there's no choice here, there's no H. The only H available is this one. Although it might be a slow reaction, it doesn't mean we can't get an E2 to happen. So the reason this is really important to bring up now, which is also good practice for the final, remember this is, when we're getting ready to do an E2, we look for our alpha beta position. Our alpha is the carbon with the leaving group. Beta is the hydrogen we're allowed to take off. There's no beta H on the other side. If we're going to do the pi bond there, since it's more substituted, we have to be worried about E and Z. How do we know? We can't just assume E because we want to avoid steric interaction. There's only one way we can do an E2, one conformation. What does the relationship of the H have to the leaving group?
That's right behind it.
Yeah, it has to have anti-coplanar relationship. How do we see that? Newman. Yes. Newman is back. So, we're going to use a Newman to help us visualize what the alkene should look like. In other words, why, if you're totally lost on what my dilemma is here, I'll draw it as a question first, and we'll circle one. So let's say I take off the, I flipped this, didn't I? Just write it so it's a little more clear. Okay, so my pi bond here, methyl, ethyl on one side. Now how do I know where my T-butyl is? Is it syn to the methyl, or is my T-butyl going to be syn to the ethyl? So that's what we have to solve, and the little margin there, I'm just going to draw one Newman that will clear it up. Because you don't get to choose E and Z based on what looks more stable. There's only one way it can actually work. So a requirement for E2 is that the leaving group is anti to the beta H, anti-coplanar. So remember how to draw your Newman. We're looking down the alpha-beta bond. So I draw in everything on the alpha-beta bond, including H's. So I'm drawing that alpha H also. I'll draw a green eye right there. That's my eyeball. I'm gonna look with my laser vision right there down that bond. So that's just to help me remember my point of view. So you're in the board now, like this. Okay, that's your eyes there. And that T-beetle's coming out of your head, and then coming out of the board on your left. See it on the end, right? So here comes the T-beetle pointing up at you above your head. Now if you get yourself on the board, who was on the left again? Turn yourself this way. Who's on your left? The leading group. And then going into the board, if the board was to melt away, I could stick my hand in there, I would grab the H. Okay, that's only halfway there, but that's a significant part of the process. We can see that, hopefully you can see it's staggered, as is the usual written confirmation. So I need to draw my beta carbon that's in the back. So just to make it clear, this is my alpha, and in the back is going to be beta. Since it's staggered, we have to fill in these bonds. So who's coming down to my feet? Ethyl. Ethyl. So the main part of the chain, if it's written zigzag, should be opposite head and feet, right? So the head was the T-beetle, the feet was the ethyl. That's that main part of the carbon chain. There's my ethyl. Who is on my left? Methyl. Right as H, right, going in the board. It's not something you can memorize, you have to work through. You can't memorize dashes are on the right, because the molecule could be flipped the other way. You could flip your eyesight, your point of view the other way. The molecule could be written vertically. You have to work through it. Okay, so remember our alpha carbon has the leaving group, and it has to be anti to the beta carbon's H. So not this H, not the H on the, not this H. That's an alpha carbon H, has to be anti to this H. Oh, we got lucky. Should have written it differently. So we'd have to rotate. Because that would also be good practice. So this is when you feel like you struck a little bit of gold solving the problem, because you didn't have to rotate, they're already anti, right? So I'll circle that. So beta H, anti to leaving group. So this is really good review for E2. Remember, they don't happen if you don't have that confirmation possible. Okay, now this is the answer to how your alkene comes in. So remember, in elimination, you eliminate the leaving group and you eliminate that H. So what's left are the R groups on one side of the alkene and the groups on the other side of the alkene. Okay, so how do you interpret this? The alpha carbon has two groups, a T-butyl and an H. So I'm going to go ahead and draw in my H on these to help answer this question. So this is my alpha carbon. That was a terrible alpha. Alpha carbon. So my alpha carbon has a T-butyl and H. My beta carbon has an ethyl and let's see, T-butyl and H, a methyl and an ethyl, right? So let me point that out. So methyl is beta, so beta's in the back, ethyl, so that's my beta carbon. So go label my beta carbon over here. Okay, so now we can see the relationship. Those green circles are circling groups that are on two different carbons. So the alpha carbon has a T-butyl that's on the same side as the beta's methyl. So that's enough to solve the problem. The alpha carbon has a T-butyl that's on the same side as the beta's methyl. So that's not true here. The T-butyl's on the opposite side of the beta methyl. Okay, so we have our answer. However, why don't we just double check that the other way was drawn correctly? In the correct answer, alkene, the alpha carbon has an H that's on the same side as the beta ethyl. The alpha carbon has an H that's on the same side as the beta ethyl. The beta ethyl is opposite the H in this one. So this would have been the incorrect alkene. So those are like the mother loads of all the E2 problems that you did back in 211. I was working through that, having to get through Newman. How come I had to do this in example B, but I didn't have to work through that at all in example A? Yeah, when you're able to get the Hoffman alkene as opposed to a Zaitsev alkene, notice the difference. Here are your beta H's. If I drew a Newman of this, I'd have all H's. Nothing to ever rotate. They're just H's, right? So no matter what, there's no relationship E and Z to establish between the H's that are here. So there's only one R group here. So I can't draw this incorrectly. So as long as I get the regiochemistry correct, I cannot get the stereochemistry incorrect. Stereochemistry on an alkene is E and Z. Regio is Hoffman versus Zaitsev. So as long as I got the right placement of the pi bond, I cannot screw up the stereochemistry because there's no stereochemistry. But if once you get to an internal pi bond, then it's tricky because the stereochemistry matters. Okay, so you don't have to take your time to draw a Newman. I mean, it's actually a good exercise to prove that to yourself. Say, oh, why'd I do that? Doesn't make a difference, right? That's always kind of a eureka moment anyway. There's nothing wrong with trying it out. But that's why I didn't do it when we worked through it the first time. Okay, so I spent a little longer on that than I normally would just because I feel like that's a valid review for 211 as well. Yes?
So the new part about this versus 211 is the bulky leaving group making the Hoffman.
Yeah, so I was going to summarize that before I go on. I just want to see, yeah, you have a bunch of little space at the bottom. So instead of moving on to this synthesis of amine, I'll make a little summary below and then we'll move on to it. Okay, so for example, I'll do it in blue just so it stands out from that previous. So E2 summary. So we're going to add to your E2 list. You have some 211 to consider with 212 now. So here we have our, you might have to write a little smaller than me because I had to see the page number there, but we're trying to work within that space. So these were on the slides, so I actually copied them so that you wouldn't have to feel like you needed to go find those old slides. So the example on the slide of the classic E2, you know, we have our KOH, we have our relatively unhindered substrate, right? And we get our internal alkene to get our Zaitsev product. So we know we go the Zaitsev route because it's unhindered base and substrate. Okay, so contrast that with the other slide where we had Hoffman example. Take a bulkier substrate, and then you take a bulkier base. I'll make it even more, you know, obviously bulky, like triethoxide. I'll move this up. So then we get our Hoffman alkene. So for Hoffman, that means we had a bulky base plus a bulky substrate. Regular old leaving group though. So this was our 211 example. So notice our leaving group was our typical halogen, or maybe something else like tosylate or whatever. But if you have an amine to start with and you really need that alkene, you don't have to find a way to replace the amine with a halogen. You can go straight to the alkene. That's the value of it. Using, so this is the difference. Why don't I use the same one as above that normally would give us Zaitsev, but instead I don't have a leaving group, I have an amine. This is the same substrate as number 1, but if I throw in step 1, methyl iodide excess. Step 2, some source of hydroxide. I'll use Klein since that's going to show up in your homework the most. So now we get a product that's different than product 1. We get the Hoffman alkene that we couldn't get from the starting material found in step 1. Okay, so that's valuable because we can actually convert an alkyl halide to an amine. So, you know, if we were stuck, we really wanted the Hoffman, but we could only get the Zaitsev, we could just take an extra step and say, well, I can convert this to an amine. We'll learn soon how. And then get my Hoffman by using a Hoffman elimination. Okay, so you don't have to have the bulky, locked-in bulky substrate, just the substrate gets bulky by making the leaving group bulky. So it's actually pretty clever. You know, all 3 aspects are altered here. And so that summarizes it all. So thank you for bringing that up, Sean. That's what I wanted to do before I move on. But we'll be coming back to it because it'll be part of our synthesis process once we learn how to make amines, which actually that segues nicely into the next section. Let's say we want to do exactly what I said, which was somehow have an amine so that I can actually access the Hoffman alkene when I couldn't, but I only have a halogen. Well, here's a halogen. Maybe I could just attack an amine with ammonium. Well, what did we just learn? When we have an amine and an alkyl halide,
It'll keep going.
it just keeps going, exactly. So we have to be concerned that we don't really get what we want there. We don't get the nicely controlled right? It can just keep going, and it can over-alkylate.
I have a question.
Yes?
Is acyl chloride considered a blocking group in this case, or it just makes it sturdy?
Acyl chloride.
Like later. Not in this thing.
Alkyl chloride, you mean?
Oh yeah, alcohol. No, acyl chloride.
We're going to get to, you mean to solve this problem?
Yeah.
We're going to get to a very specific synthesis that solves this problem. Yeah. So it's kind of, it's essentially a blocking situation. So, yeah, good call. Of course, you kind of know the pattern now. You say, oh, we're stumped. We're going to find a way to solve it, right? This is kind of the obvious first try. Nucleophile, leaving group, doesn't work. So that's not going to be the way you want to make. If we just wanted to make, what is this, 1, 2, 3, 4, butanamine, this is not the way to do it. So instead, we're going to do what's called the Gabriel synthesis. And it looks fancy, and that's because it installs, like Hava was saying, sort of a blocking group, a little mask, kind of cover the rest of the valency of the amine, so only one part of it is accessed. So, what is our little mask? It's going to be succinimide, a cheap, easily, readily obtained, commercially available starting material, also a source of an amine. I'm sorry, I was on there. There we go. Look at the 3 steps we need. We need a base. That's kind of straightforward because that's going to take off the H on the nitrogen. amide. Then we need our alkyl halide, that gets our R group on. And then we need to get rid of the mask, right? So this step helps get rid of everything else, and we get our amine, our desired amine out. So the byproduct, which we don't always show, is going to be the diacid. That's how it cleaves. It's cleaving an amide essentially. So you get to pluck that RNH2 out of that ring system here. So you get the R group on that you want, and only one, because the other two sites are occupied. And then you do the rest of the mechanism helps you get through to remove the unnecessary part and isolate just your mono alkyl amine. Okay, so of course we want to know how that works because it's not very straightforward to just see that mask on there and figure out that that would happen. So we'll go through the mechanism. I'll draw the product first since we have the template. So you see this series of steps over an arrow. You might also see something different. You might see the alkyl halide on the left and the succinimide on over the arrow, because this is truly the carbon-containing group that varies. It's the variable. You always need to use this. So you might have this over there and this deprotonated. So you don't want to be comfortable with kind of switching those around. But step one is to make the deprotonate that, so it's N-, so that it can attack and kick off, right? And then remember we remove the rest of it. And so our final product has 1, 2, 3 carbons with an amine right there. So it substitutes the halide for the amine. How does this work? First step is pretty straightforward, typical acid-base. So I'm going to draw in my lone pairs and take off the H. Normally, hydrogen's on, nitrogens are not particularly acidic, but since it's between two carbonyls, just like what a carbon is, that makes it more acidic. So we have an amide that's also been deprotonated to make a negatively charged nitrogen. So here's my nitrogen that's more nucleophilic now. Ready for step 2. It's only one equivalent, notice. That's usually specified to make sure you realize you'd want to avoid hydrolyzing the ester, right, with attacking the carbonyl. So if you just give it just enough to only deprotonate, you shouldn't have any problems. So step 2 is going to be throwing in your alkyl halide. It's an SN2 step. And we have all this spinach still attached to our nitrogen. So remember, all that's doing is tying up the other bonding sites on nitrogen so that we don't add more alkyl groups to it. Okay, so notice step 3 has a lot of the same components of step 1. So I reminded you we only had one equivalent because we didn't want to go crazy and hydrolyze the amide. Now we want to do that. We want to hydrolyze it. In other words, we want to get the carboxylic acid. So this is an old reaction. These are all old reactions. So acid base, step 1, step 2, SN2, right? Step 3, hydrolyze an amide. It's just putting it together in a sequence using succinimide was what makes it new. So I'm going to write that down. This is acid base, followed by SN2, followed by, we're going to start hydrolyzing our amide. That's why we have the excess hydroxide available now. Okay, so you're going to attack open. So O minus, OH attached. That's our new group. And then everything else is the same so far. Then we will close kick off the amide, nitrogen, so that gives us progress toward hydrolyzing one of them. Close, kick. Oops, I just drew bond still there. Okay. Close means carbonyl. Carboxylic acid accomplished there. We're left with a negatively charged nitrogen, still an amide on the bottom. Water's there to neutralize. So I'm going to show that step. Water's there to neutralize, and we get to our intermediate that's partially there. We got our carboxylic acid. We need to get to the diacid to be done, and our neutral amide on the bottom. And then it's just repeat. Once you know that missing, that sort of that key step, we're just starting to hydrolyze, you just keep repeating it until you get there. So I'm going to write that down so that when you practice it, hopefully that makes it a little more clear. So hydroxide, attack, open. I'm going to write CO2H to save some space for my carboxylic acid. So I want to focus now on the open part. We have a new OH in there. We have our nitrogen. The alkyl group attached. Okay, then we do our close kick. Close and kick. And I am going to show every little step, even the protonation steps, because it's just good practice, and I have time for today. So close, kick, we have the diacid. Bless you. I'm just going to write CO2H twice, plus the negatively charged amine, which we need to protonate to be done. So some more water comes along. And voila, we have our amine that at first glance looks like it's mysteriously formed from 6-cinnamide, but we're really only taking the NH out of there, right? The alkyl component came from the alkyl halide. The next 2 pages are all review reactions that I'm not going to take time to cover, but they also remind us how to get amines. So you might want to look over those before the next lecture. I'm just listing them there so we don't forget about them. It's, nitro group, reduce it, we have an amine. Check, right? So of course I'm not going to do mechanisms for those again, but I'm listing them there just for a reference. Be useful for your roadmap. Yes, Sam?
When you're adding water in a solution, what is the diacid do you need to nitrogen nitrogen?
You need some heat. Good question. So, Sam says, well, what's the fate of the diacid? Yeah, the poor thing, we usually don't care about byproducts, but since it's in this position where we could actually make an anhydride, they're close enough to definitely do that, if you actually need to lose water, right? So the presence of water discourages that. Usually heat is also needed. So, but if for some reason this is what you actually wanted, succinimide is a cheap starting material. You can go off and do some other things with that to get the anhydride ring, right? That kind of like the maleic anhydride in a ring that you used in your Fields Alder lab. You can get the anhydride ring if you removed water and added heat. Yeah, it's good to remember that one too. This is where I'm stopping today for amines because that's definitely kind of a doozy, and then the rest are review. I'm going to pick up with a new reaction, reductive amination, in the next lecture. So for workshop, let's do some roadmaps and a couple problems, and I'll see you soon, about 10-15 minutes if you're coming to that one.